So welcome you back to this lecture. Before I proceed further, let me recap what we did in the last lecture. So what we were dealing with in the last lecture was the scale invariant estimation. So the formulation was as follows. So what I have is I have a random vector x1, x2, xn, which could be data. This has a distribution function f, which belongs to a parametric family of distribution functions f theta, where theta belongs to 0 to infinity. So what is happening is the functional form of f theta is known. So the only unknown quantity over here is theta. So it's like I'm talking about f being distribution function of normal with mean 0 and variance theta square or standard deviation theta. Right? And what I assume is my f theta is of the type f of x1 by theta, xn by theta, where x belongs to sample space chi, which I am taking to be Rn. And I take my parameter space as capital theta, which of course from here we know is nothing but 0 to infinity. Now here f is completely specified. So the only unknown quantity is theta. So for example, as I mentioned, when I am dealing with the normal with mean 0 and standard deviation theta, my f of x1, x2, xn could be they could be independent, normal, so f of x1, x2, xn could be product I is equal to 1 to n minus infinity to xi. So that is a distribution function of xi at the point small xi, phi t dt, where this is PDF of normal 0, 1 random variable, which we call as a standard normal 0, 1 random variable. Now goal is to estimate theta to power b, where b is specified. What we saw is this in estimation problem, or this to begin with, this family of probability distributions remains invariant under a group of transformations G of BC, such that B is positive and C belongs to R. So this family of probability distribution P remains invariant under G. Now here GBC x1, x2, xn is same as bx1 plus c, bxn plus c. The vector x belongs to chi, which is Rn. B is positive, c is. So what I see is if I apply this transformation to the random vector x1, x2, xn, I again remain in this family, except that now my theta just changes. So G bar induces the group of transformation G bar on the parameter space, G of BC, B positive, C belonging to R. And what does theta becomes under the group of transformations? So that is G bar BC theta becomes B theta plus C. So here the group of transformations under which the problem remains invariant is there is only one constant. This was for a fine equivalent estimator. So this problem of from family of probability distribution remains invariant under a group of transformation GC, such that C is positive. Sorry for this goof up. But anyway, so because I know that we did in the last class, that if we apply Cx1, Cx2, Cxn, I again remain in the same family, except that, so let me write down this where GC of x1, x2, xn is nothing but C of x1, C of xn. So what it means is if I apply the transformation C of x1, C of x2, C of xn, my distribution function is again in the same form f theta, except that theta becomes now C theta. So that means G induces a group of transformations G bar C, C positive, where G bar C theta is nothing but C theta. Theta belongs to capital theta and C positive. So now I have to guess what should be my induced group of transformations on the Xn space. So first my Xn space is, because I am interested in estimating theta to power b, and theta is greater than 0, so theta to power b can take any value from 0 to infinity. So my Xn space is 0 to infinity. So let us try to guess what should be a reasonable group of transformations on the Xn space. You see, under the transform problem, theta goes to C theta. So theta to power b would go to C to power b into theta to power b. Theta to power b was the estimate in the original problem itself. So that means my group of transformations induced under the Xn space would be G tilde C's, where G C tilde A. What does it become? Because theta becomes C theta, so theta to power b would become C to power b theta to power b. So that means C to power b, and theta to power b was the original estimate, so it is C to power b A. A belongs to A, and C is positive. So my problem remains invariant under this. Now L theta A is invariant. We saw that if and only if L theta A is same as W of A theta to power b, theta greater than 0, A greater than 0, for some W which is non-negative. Right? What we have assumed was W of e to power t is convex and non-monotone. This is not required in general. For example, square error loss function, which is W of t is equal to t minus 1 whole square, does not satisfy this, but still minimum risk invariant estimator exists in that case. What it only ensures is that if you assume this, then the existence of MRE is guaranteed. Okay, so this is the thing. So I take my loss function to be this, which is of the type W of A by theta to power b, and I say that di is the class of all invariant estimators. Then what we saw was delta belongs to di. Invariant estimators which are non-randomized. Because we have said that normally we'll take our loss function L theta A to be such that W of A by theta to power b is convex in A. So delta belongs to di if and only if delta of x is same as mod of xn to power b by u of z1, z2, zn minus 1 and zn. And what was these zi's? Zi's was xi upon xn for I is equal to 1 to n minus 1, and zn was nothing but xn upon mod of xn. What we also saw that this whole z1, z2, zn minus 1 in this case is ancillary. So then the question arose, mod of xn to power b is a scale invariant because if I apply cx1, cx2, cxn, it becomes c to power b mod of xn to power b. So the question is, if I replace this mod of xn to power b by any invariant estimator delta naught, then that also characterizes the class of all scale invariant estimators. So let delta naught belonging to di be fixed. Then what we saw was delta belongs to di if and only if delta x. So there I can replace mod of xn to power b by delta naught x. For some u. For some function u. All right. So then we saw that a result which says that for every fixed z, which was belonging to z1, z2, zn minus 1, can take any value, because these can take any value in R. So z1, z2, zn minus 1 belongs to R. Zn, which is xn upon mod of xn, can take only value in minus 1 to 1. Let u star, which is u star z, minimizes psi u, which is expected value of theta is equal to 1 and delta naught x, w of delta naught x upon u, given z is equal to z. Then MRI is, let me call this as delta star x, which is delta naught x, this delta naught which was fixed, divided by u star z. Now, in case of squared error loss function, we saw that this reduces so for Wt is equal to t minus 1 whole square. That means my L theta a is nothing but a by theta to power b minus 1 whole square. So that is L theta a is same as a by theta to power b minus 1 whole square, a positive, theta positive. In this case, MRI is that we saw last time. Delta naught x, and then expected value of theta is equal to 1 of delta naught x given z is equal to given z, given e theta is equal to 1 delta naught square x given z. Right? In the case of squared error loss function, what we saw is minimizing u star is given by this, the quantity over here. Okay, so if in particular I take delta naught x to be mod of xn to power b, so it becomes mod of xn to power b, because I can take delta naught to be mod of xn to power b because mod of xn to power b is invariant estimator. So this is same as e to power theta is equal to 1 mod of xn to power b given z divided by e theta is equal to 1 mod of xn to power 2b So what I'll do is, this is where I left yesterday. So what I'm going to do now is, I'm trying to derive what these expressions are. For that, I'll need the distribution of, conditional distribution of xn given z1, z2, zn minus 1, and zn. So what I'll do is, first I'll try to find out the conditional distribution of xn given z1, z2, zn minus 1, because zn only gives me the sign of xn. So let us first try to find out what is the distribution of, conditional distribution of xn given z1, z2, zn minus 1 under theta is equal to 1, because I need only expectation under theta is equal to 1. So let f be the PDF corresponding to distribution function f. Note that distribution function f corresponds to f of theta is equal to 1, because f of theta is equal to 1 is nothing but only f of x1, x2, xn. Then, so joint PDF of x1, x2, xn at theta is equal to 1 is f of x1, x2, xn, where x belongs to R. Now I have is z1 is x1 upon xn, zn minus 1 is xn minus 1 upon xn. Zn let me put as, Zn is xn upon mod of xn, but let me put another variable, xn as xn itself. Right? So let's make this transformation. With this transformation, what do I get? x1 becomes z1 times xn, x2 becomes z2 times xn, xn minus 1 becomes zn minus 1 times xn, and xn becomes as xn only. So first thing is I should try to find out what is the Jacobian of a transformation. Del x1 by del z1, which is xn, del z2, 0, 0, and then del x1 by del xn, which is z1. Del x2 by del z1, 0, del x2 by del z2 is xn, 0, 0, 0, z2, then 0, 0, 0, xn, zn minus 1, 0, 0, 0, 0, xn. So it becomes just mod of xn to power n. So first I try to find out so joint PDF of let me call this as z1, z2, zn minus 1, and xn is, so let me call this as f of z1, z2, zn minus 1, xn. z1 is fixed at small z1, zn minus 1 is fixed at small zn minus 1, and suppose xn is fixed at t. So what is the Jacobian of a transformation? Mod of xn to power n. So xn is fixed at t, so it becomes mod of t to power n. Right? I have to put a modulus of Jacobian. Then joint PDF was f. So here I make those transformations. F of x1 is fixed at small x1. This has t. So x1s become z1 times t. Then xn minus 1 is nothing but zn minus 1, small zn minus 1, times xn, which is fixed at t. And then xn, which is t. And certainly, since these xi's belongs to R, and so I put z1, z2, zn minus 1. What I have to find is conditional Pdf of xn given z1, z2, zn minus 1. So conditional distribution of xn given z1, z2, zn minus 1 at the point, let us say t, and z1, z2, zn minus 1 is fixed at z1, z2, zn minus 1. Now I know that conditional is same as the joint divided by marginal of z1, z2, zn minus 1. Marginal of whatever is given. But this is given, so it will be a constant. So that means conditional PDF is always proportional to the joint PDF, except that that constant of proportionality would depend on this marginal z1, z2, zn minus 1. So it would be some c of z1, z2, zn minus 1. Let me put as c1 of z1, z2, zn minus 1. And then the joint PDF of all that, z1, z2, zn minus 1 and xn, so which is nothing but over here, mod of t to power n, f of z1 t, zn minus 1 t, t. And here t belongs to R. For any fixed z1, z2, zn minus 1, this is a joint PDF of xn given z1, z2, zn minus 1. Now note that what I need to find out is, what is a joint PDF of xn given z1, z2, zn minus 1 and zn. Now zn is xn upon mod of xn. It takes only two values, minus 1 or plus 1. So it is minus 1 if xn is negative and plus 1 if xn is positive. Over here z1, z2, zn minus 1 is given. If zn is also given, it only tells me what is the sign of this xn. Now let me pose a question. So suppose x has PDF G. What is the conditional PDF of? X given that x is less than 0. The probability distribution is going to be same, except that now it would be concentrated on t less than 0. So it is going to be g of t divided by, you have to normalize it, x less than 0, so minus infinity to 0, gt dt. Here you can put gy dy. Right? Because now you have a prior information that x is less than 0. So this is what PDF is. You can derive it easily. It is a standard thing. So here, if I add over zn could be minus 1 or 1. So my PDF is going to be exactly the same, except that t gets divided by minus infinity to 0 in the denominator. So what I do is, using this from here, I get, so f of xn given z1, z2, zn minus 1 and zn, xn at t, these at z1, z2, zn minus 1, and let me first put zn as minus 1. Zn is minus 1, that means xn is negative. So that means this argument is negative, so the PDF is going to be the same, except that now I'll have to add the normalizing constant that t is less than 0. So this is same as C1 of z1, z2, zn minus 1 mod of t to power n minus 1 f of z1 t, Zn minus 1 t t divided by normalizing constant. So it would be same thing from minus infinity to 0 of this variable has to be integrated. So this would be there in the numerator and denominator both the side. So this gets cancelled, and I can replace this by just minus infinity to 0 y to power mod of y to power n minus 1 f of z1y Zn minus 1 y dy. By the same logic, what is the conditional Pdf of xn given z1, z2, Zn minus 1? Now suppose Zn value is plus 1. So this is t z1, z2, Zn minus 1, 1. The same thing except that now this normalizing constant would be from 0 to infinity. Now here the range of t is less than 0. Otherwise the Pdf is 0 because this is a range where Zn is minus 1, that means xn is negative. Now in this case range would be t positive, so this is same as mod of t to power n minus 1 f of z1t Zn minus 1 t divided by 0 to infinity mod of y to power n minus 1 f of z1y here range is positive. Good. So I have now derived the conditional Pdf. What I need to do now is I have to just find out those expectations. So what I know is my delta star x I know is nothing but mod of xn to power b into e theta is equal to 1 mod of xn to power b given z by e theta is equal to 1 mod of xn to power 2b given z. So for Zn is equal to minus 1, that is, if you are given that xn is negative, let us try to see what is this quantity. E theta is equal to 1 mod of xn to power b given z by e theta is equal to 1 mod of xn to power 2b given z. Now when Zn is minus 1, my conditional Pdf is given by this. Now note that numerator and denominator, because this term which is a normalizing constant, it does not depend on this t. This will come in the numerator as well as denominator over here, so that just vanishes. So what I am left with now is, this is same as minus infinity to 0 mod of t to power n minus 1 f of z1t z2t Zn minus 1t. Z1 is nothing but x1 upon xnt. Zn minus 1 is nothing but xn minus 1 upon xnt. T dt. These are Pdf, but I have to find expected mod of xn to power b. So it becomes mod of t to power n minus 1 and mod of t to power b. So that becomes mod of t to power n plus b minus 1 divided by minus infinity to 0. Here mod of xn to power 2b. So that is mod of t to power 2b, and mod of t to power n minus 1 will come from here, so it becomes mod of t to power n plus 2b minus 1 f of x1 upon xnt Now note that this is for the situation when xn is negative. What I can do is I can throughout make the transformation t upon xn is equal to t prime. And then again, I can replace t prime by t, because t prime is finally an integrating variable. So I make t by xn as t prime, both in the numerator and denominator, and then I can replace t prime by t. So if I do that, what does that become? First, let us try to see the range. Now note that xn is negative. So when t is negative, t is minus infinity, and xn is negative, it becomes infinity. And when t is 0, t prime is 0. So its range becomes 0 to infinity by virtue of the fact that xn is negative. Then mod of t becomes mod of t prime, which I again replace by t, mod of xt times xn to power n plus b minus 1. F of t by xn I have put as t prime, which I will again replace by t, so it becomes f of x1t. Second row also t by xn is t prime, so that becomes x2t. T by xn is again t prime, so xn minus 1t. And finally t is nothing but xn times t prime. So it becomes xn times t. There will be one Jacobian term, dt as mod xn dt prime. So mod xn dt prime, t prime I have replaced by dt. Same thing in the denominator, except that it becomes 0 to infinity, except that because here mod of t to power n plus 2b minus 1 was there, so it becomes mod of t xn to power n plus twice b minus 1. F of x1t, x2t, xn minus 1t, xnt, mod of xn dt. Okay, so we have simplified this at least for the case xn is positive, xn is negative. So what does that become? This becomes mod of xn to power n plus and mod of xn to power. So it becomes 1 upon mod of xn to power b. And this, since it is over here, that will get cancelled with that. So 0 to infinity. Now here t is positive, so mod of t I can replace by t itself. So t to power n plus b minus 1. F of x1t, xn minus 1t, xnt dt, 0 to infinity, t to power n plus 2b minus 1, so when I calculate delta star x, this gets cancelled and I exactly get this. So let me just use this space. So delta star x when xn is negative is basically this quantity, 0 to infinity, t to power n plus b minus 1, f of x1t, xnt dt divided by 0 to infinity, t to power n plus 2b minus 1, f of x1t, xnt dt. So for xn less than 0, we have derived this expression. Now what we'll see is when xn is greater than 0, you'll exactly get the same expression. How do you get it? Now note that when xn is less than 0, greater than 0, now this range would become 0 to infinity over here. That means Zn is equal to 1. So this will become 0 to infinity, this becomes 0 to infinity. You repeat exactly the same things. And again you get the same expression, where xn is positive or xn is negative. So what you get is, so you can see there is no change anywhere, because except that the first expression would be 0 to infinity. This would be 0 to infinity because I will get a different conditional PDF in this case. I make again the same transformation. But here Zn is 1, that means xn is positive. So range 0 to infinity, because xn is positive, the range 0 to infinity here would remain 0 to infinity only. And rest of the things are as it is. So for L theta E as a by theta to the power b minus 1 whole square, a positive, theta positive. The minimum risk is delta star x, which we have found out is 0 to infinity t to the power n plus b minus 1 f of x1t xnt dt divided by 0 to infinity t to the power n plus twice b minus 1 f of x1t. So in the case of squared error loss function, which is of this type, I am able to get delta star x in a closed form. But note that I have observed that in situations where complete sufficient statistic exists, then you choose one invariant estimator delta naught, which is a function of a complete sufficient statistic. And since Z is ancillary, one can immediately get the MRI, and one doesn't have to deal with the conditional distribution, because if one has to find out this may be complicated, because finally you have to do f of x1t. If not difficult, it could be tedious. So that's, but this formula could be useful in situations where complete sufficient statistic does not exist. Minimal sufficient exists, but complete sufficient does not exist. If complete sufficient statistic does not exist, I cannot conclude from Bossieu's theorem that Z and they would be independent. So finding a delta naught based on a complete sufficient statistic approach may not work. So in that case, I have a ready-made formula. I can use this. Or even in situation where complete sufficient statistic exists, there is a possibility that the distribution is very complicated. Okay, so let us try to, so for example, when you're talking about uniform theta minus half to theta plus half, it is a location family, but complete sufficient statistic does not exist, because you can get a function of first order statistic whose expectation give you some function of theta. You can get a function of the largest order statistic whose linear combination will give whose expectation will give a function of theta. Then you can use the linear combination of x1 and xn, so that linear combination of x1 and xn has expectation 0. But probability that that linear combination would be 0 is 0. So in those situations, this kind of a thing would be useful. For example, uniform minus theta theta. Uniform minus theta and theta, x1 and x first order statistic and largest order statistic are minimal sufficient, but they are not complete sufficient. So I cannot use the Bossieu's theorem. So in that case, this ready-made formula turns out to be useful, but wherever you have a complete sufficient statistic and whose distribution is tractable, One should use the other approach. So let's take one example.